The next part of our journey in dynamics, we're going to start to talk about friction in a bit more depth. Now, we've already addressed friction to some extent when we've talked about it using the Atwood's pulley, the Fletcher, or not so much the Atwood's pulley, sorry, the Fletcher's trolley and other situations where we've used Newton's second law. But this time, we're going to do a little bit more with introducing things like coefficients of friction and all that. So we're going to talk a bit more about that in the next couple of videos, or the next few videos. So friction, as we've discussed already, it's going to be a force that occurs between two surfaces when they're trying to move relative to one another. And what's going to happen is friction is always going to be in the direction opposite to the motion. Or we could also say that it's opposite to the direction of intended motion. So when we mean intended motion, if the object's not moving, where would it go if there was no friction? This is more for inclined planes. But as I said, we'll discuss that a little bit later. So we're going to look at two different types of friction for the rest of the course. We're going to look at static friction, and we're also going to look at kinetic friction. So let's first talk about static friction. So the word static means rest or not moving. So when we're talking about the force of static friction, we're actually talking about an object that is at rest. So static friction's job is to actually prevent the object from moving. Now, a really important thing with static friction is that its magnitude, it does not have a fixed value. The value of static friction is going to change until the object starts to move. So we want to think about it, I don't know. I'm going to have to do my best to try and show you this in a bit of a digital environment. So, I have my calculator here. I give it a little push. There's a force of static friction that's going to match the force of that push I made. Object didn't move. I'm going to push it a little harder. So it did move. Let me see. Now, I'm going to try and tap. I try to tap it a little bit harder. At some points when I tap it a little bit harder, it doesn't move. When I tap it a bit harder, it still moves. But the point is, like, for example, if I push on something, let's say I apply 100 newtons of force on an object and it doesn't move, the force of static friction is going to be 100 newtons. It's going to counteract that exactly. Let's say I apply a bit more force. I apply 200 newtons worth of force. Object doesn't move. Well, the force of static friction is going to be 200 newtons to counter that. All the force of static friction is going to do is try to counter my applied force. And it's going to continue to counter that, and it's going to continue to change up until the point that we start to move. So what we're really going to be looking at when we talk about static friction, we're going to be looking more at the cases of the maximum value of static friction. So we're going to be kind of looking at that case, like how much force can be applied just before the object starts to move. So you don't have to worry too much about static friction having a non-fixed value, but it's just something I wanted to point out. Once the object does start to move, however, then we switch our discussion from static friction to kinetic friction. So when we are analyzing problems involving static friction, because the object's not moving, we get to immediately talk about the net force being zero. And we love static friction problems for that reason. So if the object is in one special case, if the object is experiencing static friction and it's on an inclined plane, the force of static friction is always going to be directed up the plane. What it's trying to do is it's trying to impose the direction of intended motion. If we had an object on an inclined plane, it would like to go to the bottom of the plane. What we're doing here by what static friction is going to do is it's going to try to prevent that. So if the object wants to go down the plane, static friction is going to go up the plane. And we can look at a nice quick example of that. So we have a very outdated iPhone 7. It's got a mass of 172 grams, and it's at rest on an incline of 30 degrees. So we want to determine the magnitude of the force of static friction that's acting on this iPhone. Alright, again, a lot of the times with the inclined plane problems, I do like to sketch it out. Why? I don't know, but I just like to do that. So here's my lovely inclined plane. Here's my 30 degrees. Here's my phone. We're going to treat it like a brick. Now, a couple of things. First of all, my mass in grams, I don't like that. To go from grams to kilograms, we're going to divide by 1,000. So this is really the same as 0.172 kilograms. That's important. And yeah, that's pretty much the only main thing. And then, of course, being at rest, keyword, this is not moving, we get to say the net force is 0. We really love that. So let's draw our free body diagram. So our free body diagram for this object, so here's my iPhone, we're going to represent it as a dot. So we're going to have this force of gravity that's going down. And then we're also going to have this normal force that is acting perpendicular to the surface. And then we're told that there's friction this time. So the phone wants to go down the plane. So friction's going to have to go up the plane in order to oppose that. So our force of friction, we're just going to make it look a little bit like this. So we're going to put FF. And I'm going to put a little S for force of static friction. You don't actually, as long as you put force of friction, that's all we're looking for. If you forget to distinguish whether it's static or kinetic, not a big deal. Now again, with inclined plane problems, we want to make sure that we set appropriate conventions, and we also want to make sure that we break down our force of gravity. So for the conventions, I'm going to say down the plane, we'll call that positive, and we'll say perpendicular to the plane, we'll also call that positive. And my force of gravity, again, we can break that up into two components. We can break that up into the force of gravity perpendicular to the plane, and we can also break this up into a component, force of gravity parallel to the plane. Now for us, what we're interested in the moment is we're interested in this direction parallel to the plane. We want to find the magnitude of the force of static friction. This is acting parallel with the plane, so that's what we're going to look at. So we're going to look at the net force parallel to the plane. So parallel to this plane, I'm going to have this force of gravity parallel, because this is the piece acting parallel to the plane. And then I'm going to have this force of static friction. Now, again, the net force on this object is going to be 0 since it's at rest. So we don't actually have to consider this term. This is nice. We like that. So we're going to have Fg parallel plus force of static friction equals 0. So what we know is that the force of static friction, this is going to be the negative of the force of gravity parallel. And we have definitions for these. So we know that the force of gravity, or the parallel component of it, we know that this is mg times sine of the angle. So the last thing we need to do is we need to calculate this. So we have that mass, make sure it's in kilograms, so we have that 0.172 kilograms. Now, because we've called down the plane positive, and our component of gravity would be acting down the plane, we're going to treat g as positive 9.81. So this is going to be positive 9.81 meters per second squared, and then we're going to put in sine of 30 degrees. So again, we want to make sure we have positive g. We're going to multiply that by our mass in kilograms, and we're going to multiply it by sine of 30. Make sure that your calculator is in degree mode. So if we're really careful with the calculations here, we are going to get about, let's see here. We're going to get about 0.844 newtons negative. The negative, again, if we're looking at the direction parallel to the plane, if I get a negative, that's just telling us it's going opposite to this. So instead of being down the plane, it's going to go up the plane. That's good. That's consistent with our free body diagram. But we're only looking at the magnitude, so we don't care about direction. So we're just going to say that the magnitude of the force of static friction is about 0.844 newtons.